and this is lecture 13 on atomic and molecular physics. And today we are going to study Stern and Gerlach experiment, which is wonderful experiment. So, what is the need of Stern and Gerlach experiment? So, this experiment is the first and direct experimental demonstration of spin of electron and spin magnetic moment. So, how is the experimental arrangement and what are the observations for this experiment? So, experimental arrangement looks like this. It is a oven. Here you can see oven where we vaporize silver atoms. I will be telling you why we have selected silver atoms later on. So, here there is a oven where we have silver atoms which are vaporized. S1 and S2 are the slits. They are used so that we get a collimated beam of silver atoms, or you can say one silver atom at a time. Then here we use magnetic field, and this magnetic field which we apply, it is inhomogeneous or it is non-uniform in nature. So why we cannot apply uniform field, or what, why there is a need of inhomogeneous or non-uniform magnetic field, that also I will discuss. So here this non-uniform magnetic field, it is produced with the help of this kind of pole pieces of the magnet. So here you can see that one pole piece of a magnet, it is in the form of a triangle, another pole piece, it is having such kind of a geometry, and then there is a photographic plate where we will be seeing the trace of silver atoms. So silver is vaporized by heating it in a small oven O. A narrow beam of silver atoms is obtained by using slits S1 and S2. It is then passed through an inhomogeneous magnetic field, and after passing through magnetic field, the beam falls on the photographic plate, and this entire apparatus is kept in an evacuated chamber to avoid collisions and scattering. Now let's see. Now here the inhomogeneous magnetic field which we produce, it had a very steep gradient in the vertical direction, and here the vertical direction we will be calling it as a x-axis. So it was produced by specially designed pole pieces of an electromagnet. One pole piece is in the form of a triangle, or you can say knife edge, and another pole piece had a chamber cut in it parallel to the knife edge. You can see here there is a cut here. Okay, now here when we have this kind of magnets, whatever magnetic field will be there, it will be much more intense near the knife edge and than anywhere else in the gap. And without any magnetic field, we get a thin line of trace of silver atoms on the photographic plate. But when we apply magnetic field, then the trace of silver atom, it splits. It splits into two lines of almost equal intensity. So something like this. So without magnetic field, you just get a straight line, trace of silver atoms. But when you apply magnetic field, you get splitting. Now here if you will see the splitting of this lines, at the center the splitting is maximum, and towards the end we are getting lesser splitting here, because when we are applying the magnetic field, the magnetic field, it is in such a way that it is more intense at the knife edge, and at the points, at the ends, it is having lesser magnetic field. Now we know that splitting of magnetic lines, it takes place in the presence of strong magnetic field. That is what we call as a Zeeman effect. And when the magnetic field is weak, then the tracing doesn't splitting doesn't take place. That is what the anomalous Zeeman effect is. So here, as the magnetic field is weak over here at the edges, and that is how the splitting is not taking place. Okay, so in the experimental arrangement, the variation of field in y and z direction we have considered as negligible, while we are just considering the x component, which is in the vertical direction. Now why we are choosing silver atoms? When we choose silver atoms, they are in the not they are in the s state, and for silver atoms L is 0. As L is 0 for silver atom in ground state, therefore the magnetic moment, orbital magnetic moment, that is also 0. So when we have orbital magnetic moment as 0, that means whatever magnetic moment we will get in this particular experiment, it will not be because of the orbital motion. That means it is because of the spin motion, and that is what we are trying to find out. Okay, so the additional magnetic energy of silver atoms is given by the formula V. It is equals to 2 EH cross upon twice m into BMS. We have already seen this formula in the earlier lecture. And here, since B is inhomogeneous, or you can say non-uniform, therefore whenever you have a uniform field, it will not be able to it will be just able to precess the magnet, or it will be able to twist the magnet. But when you have a inhomogeneous field, then the magnet, the two forces acting on the two poles of the magnet, they are not equal, and that is how a force acts on the silver atoms in x direction. So we have force is equals to minus 2 EH cross upon twice m, and here this f is minus dv by dx, right? So that is how I have taken differentiation of this. So 2 EH cross upon twice m ms, these quantities are constant, so I will be taking differentiation of only b. So that is how I got f is equals to minus 2 EH cross upon twice m dB by dx into ms. So now if our spin hypothesis is acceptable, then ms can take only two values. One value is plus half and another value is minus half. So for these two values, the force will be in opposite directions. Silver atoms have equal probability of having ms half and minus half, and that is how we are getting that kind of a splitting. So we expect to observe the beam splitting up into two equally intense beam, and this indeed is observed in Stern and Gerlach experiment. So if we consider that spin quantum number s, it is not equals to half, then ms would not take up only two values, and number of its components will not only be two. Also note that if electron did not possess spin, if the electron doesn't have any kind of a spin, then we should not get any spin angular momentum. But in this experiment, when we have considered silver atoms which is not having any orbital moment, we are still getting the value of moment. That means it is because of the spin motion. So that means electron did possess spin. There is a spin magnetic moment of the silver atoms, and that is how we are getting splitting because of the spin motion. Now what we conclude in this experiment, an electron possesses spin. The spin quantum number has a fixed value, and that value it is equals to half, and the spin it is associated with a magnetic moment, spin magnetic moment. Now again I'll come to this question, why silver atoms are used in this experiment. So we know that if you know that silver atom has 47 electrons, 47 protons, that means atomic number of silver it is 47. So 47 electrons, 47 protons, and silver has 60 or 62 neutrons depending upon which isotope we are considering, and the magnetic moment depend on the inverse of the particle mass. So we know that mu L it is E upon 2m, right? You remember that formula, mu is E upon 2m into L. That is the formula for magnetic moment. That means it is inversely proportional to m. Now when we consider the magnetic moment, we know that mass of a proton and mass of a neutron, it is approximately 2000 times mass of electron. So as the mass is large, so it will have a little effect on the magnetic moment of the atom. So we neglect them. So from your study of the periodic table in chemistry, you recall that silver has an electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10 and 4p6, 4d10, 5s1. That means silver has one unpaired electron, which means that there is only one 5s electron outside of the closed shell. Now, the electrons in the closed shells can be represented by a spherically symmetric cloud with no orbital or intrinsic angular momentum. So here the 5s electron which we have, it is unpaired electron. That means it is in the ground, it is in the s state. We know that for s state L is 0, so there is no orbital motion. So whatever effect we are getting, that means it is because of the spin motion only. So that is why we have chosen silver atoms, as it has one unpaired electron and it is in the s state. So that's all about Stern and Gerlach experiment.